So this is question number 2. It says you're given y1. So you're given y1 as the solution of the homogeneous the homogeneous differential equation. As it says, the associated homogeneous equation. That's when this equals 0. They now say you use the method of reduction, of order, to find a second solution y2 of the homogeneous equation and a particular solution of the given homogeneous equation. Okay, anyway, before we start doing anything, let's start by writing down the differential equation that we're given. So let me say solution. Now we're given y prime prime minus 3y prime plus 2y equals 5e to the power 3x. So this is what we're given. And then we're told that y1 equals e to the power x is a solution of the associated homogeneous equation. Now we want to use the method of reduction of order to find a second solution that satisfies the same homogeneous differential equation that y1 satisfies, and then from that same solution we should find a particular solution of the homogeneous equation. Now the thing is that to find, since we're told to also find a particular solution, now what you'd observe is that what we have on the right hand side here is not 0. So this is a non-homogeneous differential equation. So what we're going to do is that in trying to find y2, we will not set this to 0, but we're going to solve it like that. So like we're solving a non-homogeneous differential equation, and then you're going to see the form of solution we're going to obtain. Now it is most likely the kind of solution we're going to obtain is going to contain both the particular solution and then a general form of the second solution that complements y1. Okay, in other words, like we've been doing so far, so let's make y2, you can say let y2 equals, so u of x times y1, and u, that's u times e to the power x. So this is our y2. Now find y2 prime and y2 prime prime to satisfy this differential equation. So we have y2 prime to be u prime e to the power x plus u e to the power x, and then we find y2 prime prime, so which is going to be, I'm going to skip steps here, that's u prime prime e to the power x plus 2u prime e to the power x plus u e to the power x. So this is what we get for y2 prime prime and all this. So the next thing is we substitute all of them into here. So on making a substitution, we have y prime prime, so this is my y2 prime prime, so that'll be u prime prime e to the power x plus 2u prime e to the power x plus u e to the power x, then minus 3 times my y2 prime, that's u prime e to the power x plus u e to the power x, then plus 2 times y, this is my y here, plus 2 times y, that's u e to the power x. Now all equals 5e to the power 3x. So this is quite different from the ones we've been doing so far. The ones we've been doing so far, they have the right hand side to be 0, but here it is not 0. So let's continue. Now when we simplify this whole thing here, what we're going to have is u prime prime, so this implies u prime prime e to the power x minus u prime e to the power x equals 5e to the power 3x. This is what we're going to obtain. So now as usual, we'll make a substitution. So we'll say let w, so let w equals u prime, then w prime would be u prime prime, then from there on we continue. So w prime is u prime prime, so this becomes w prime e to the power x minus, so u prime is w, that's w e to the power x equals 5e to the power 3x. So this is a linear differential but non-homogeneous differential equation. So you're writing this, we have dw dx. So I'm going to divide both sides by e to the power x, so you have minus w equals 5e to the power 2x. And then the integrating factor here is going to be e to the power, so what we have here is -1. So that's minus 1 dx, and that will be e to the power negative x. So we multiply both sides of the differential equation by the integrating factor. So we have e to the power negative x, the w dx, then minus e to the power negative x w equals 5e. So e to the power 2x times that is going to give us 5e to the power x. So let's continue. So this could be written as, like we've done so far, which we've explained in the past videos. So it's going to be ddx of e to the power minus x w equals 5e to the power x. So we want to find w, so we integrate both sides. So it's going to give us e to the power minus x w equals the integral of 5e to the power x dx. So, and then this is the same thing as 5e to the power x plus c1. So that is to say e to the power negative x w is this. So this implies that w equals, so we multiply both sides by e to the power x. So we have 5e to the power 2x plus c1 e to the power x. So this is our w. So but then our w is u prime. So we're going to write u prime, which is going to be du dx equals 5e to the power 2x plus c1 e to the power x. So to find u, we integrate both sides with respect to x. That's 5e to the power 2x plus c1 e to the power x dx. So when you integrate both sides, you have 5e to the power 2x divided by 2 plus c1 e to the power x, then plus the arbitrary constant, which is c2. So this is going to be your final solution for your u now, right? So this is going to be for our u. But then we have that our y2 equals u times e to the power x. So that implies that, so I'm using this here, right? So that implies our y2 equals u. So our u is this times e to the power x. So that's e to the power x times 5e to the power 2x all over 2 plus c1 e to the power x plus c2. So this is what we have for our y2. And then if we expand this, you have y2 equals e to the power x times this. So that gives us 5e to the power 3x divided by 2 plus c1 e to the power 2x e to the power 2x plus c2 e to the power x. Now there's something you observe. In this solution here, like the other ones we've been getting, we do not have each of the terms of y2. They are arbitrarily rendered. In other words, here they have arbitrary constant, but here is of the form of a particular solution. So that's what you observe here. So if you observe closely, you see that there is no arbitrary constant here. So that tells us that this is representing yp. So while this is representing like something like yc, something like that. So from here, I could infer that the particular solution of that non-homogeneous differential equation, that is yp, is going to be 5e to the power 3x divided by 2. And then for the other part, which is our y2, so which we're going to call, I'm just going to call it yc for now, which is going to be c1 e to the power 2x plus c2 e to the power x. But then we'll recall that the question says find a second solution. So they don't need a general form. They just need a single solution. Since they need a single solution, so we're going to replace the arbitrary constant here by some numbers. So you could choose anything, but then you have to be careful. You not just choose C1 and C2 randomly. So we know that according to what we have here, our y1 is e to the power x. So we're given that y1 equals e to the power x. So any kind of number you're going to substitute for C1 and C2, it shouldn't be the same thing with e to the power x, or else they're going to be multiples of each other. So because our aim of finding a second one that complements this must be linearly independent. So in other words, I'm going to set this to, I can set this to 0 and set this to 1. So we have our second solution, which I'm going to call yc now. So my yc is y2 now, e to the power 2x. So this is going to be my y2. So my y2 is e to the power 2x, and then a particular solution which I'm told to find is, which is what is here, is 5e to the power 3x divided by 2. So this is our solution, and then that completes the problem.